Hello, welcome to Calculus 2. In this first video, I'm going to describe a major motivating example, well, really a sequence of examples, that I'm going to use to motivate the main idea that ties Calculus 1 and Calculus 2 together and will be the big area of study for most of the Calculus 2 course that we're in. And hopefully this will also refresh your memory about some mathematical terminology and concepts and things that you may have seen before, thought about. And really this is just going to get our brains moving again in a mathematical way. So for this example, well, this sequence of examples, I want you to imagine that I have some kind of apparatus that allows me to roll a marble back and forth along a straight track. So try to imagine something like, a wooden train track, like a toy train on the top of a table, and there's some metal marble there, and somehow I have, I don't know, the details aren't super important here. I have a remote control, or, like Bugs Bunny, I've got a big magnet under the table and I'm moving it back and forth. Something. Again, the details are not super important, but what I want you to imagine is that I am able to control the velocity, how fast the marble is moving at any moment in time. So I can send it moving to the right, and I can control how fast it's moving, and then I can make it turn around and come back to the left and change its velocity. Just pretend that I'm able to control those kind of things at all moments in time. And then our goal is going to be to explore how my control of the velocity, how fast the marble is moving, how that affects how far the marble is traveling, the displacement. So let me outline some of these vocabulary terms that we're going to use a lot, because in colloquial language, we might tend to use velocity and speed almost interchangeably, as if they mean the same thing. But in mathematics and physics, they have a slight distinction. So first, the velocity is what you think it is, how fast the marble is moving at any moment in time. But we allow it to be signed, S-I-G-N-E-D, signed. It can be positive or negative. And for our setup, because I have a single straight line track where I can send the marble moving to the right or to the left, let's just agree that motion to the right means positive velocity, whereas backwards motion to the left means a negative velocity. Kind of like how along the x-axis on a graph, we have positive x values to the right and negative x values to the left and 0 right in the middle. Meanwhile, speed is the absolute value, the magnitude of the velocity. So it's something that will never be negative. It will always be 0 or positive. So as an example, if I'm sending the marble moving off to the right at, let's say, 3 feet per second, that would be a velocity of positive 3, and therefore a speed of 3 feet per second. It tells me just how fast it's going, but it doesn't care which direction it is. And so at the same time, if I send the marble off to the left at 3 feet per second, that would be a negative velocity, but I would still call it a speed of 3 feet per second. And so this is kind of like how we talk about speeds colloquially. If I tell you I was driving my car at 30 miles per hour, you know how fast I was going. I just told you the speed. You don't have to ask me, well, were you driving north or west or south? You understand how fast I was going because I told you the speed. And very similarly, like we have velocity and speed for the rate of change of the motion, we also have these two terms, displacement and distance, for how far the marble is traveling. And so displacement is going to be a net change, a total change in location. That's also going to we're going to allow it to be signed, positive or negative, kind of like velocity is. So for example, let's say I send the marble rolling off to the right 10 feet, and then I send it moving backwards to the left 15 feet. So if I were to diagram that out, here's my straight line track. Here's my marble here. And let's say I send it going 10 feet this way, and then I send it going back 15 feet this way. Well, in total, it's going to end up 5 feet to the left of where it started, because it goes 10 feet right, then it comes back, and then it keeps going another 5 feet, the difference between 10 and 15. And that is the displacement. It's the net change in location. and the negative is what's telling you that it's off to the left of the starting point. In my x-axis analogy, this is kind of like saying, well, the marble is at x equals -5 now. It's to the left of 0, where it began. But meanwhile, we know that it traveled 25 feet total to do that, and that's what the distance is. So in a way, the speed is the absolute value of velocity, and very similarly, the distance is kind of like the absolute value of the displacement, but of each segment, kind of each component. I had to take the 10 and the 15 and add them together, both positive. Now, continuing to use my car analogy, the displacement is kind of like your GPS. It tells you where you are, but not necessarily how you traveled to get there. So when I open my GPS app, it tells me where I am and how far away I am from home, but doesn't necessarily tell me how far I've traveled that day to get there. That is what the odometer in my car does. It keeps track of how many miles I've traveled, and that's more like what the distance is. All right, so now that we have some vocabulary terms, let's apply that to a specific example, or really we're going to do a few examples in a row. So I have my details of the example here covered up in the black box, which we'll reveal in a second. But for now, I want you to think about this and pause the video in a second. Let's suppose I set the marble rolling off to the right, and I'm controlling the speed, and so it's a constant 4 feet per second traveling to the right. What happens during the first 6 seconds? How far does the marble travel? What's its displacement? What's its distance? And perhaps, can you think about how to represent this using a function or a graph of some kind? And can you think about how your answer to this question is related to that function and its graph? Pause and think about this for a minute and then come back. Okay, let's look at the details. The key idea that we need to use here is that distance is the product of rate times time, and that works for a constant velocity, which is what we have here. I said, let's set the marble rolling to the right at the constant speed, the constant velocity of 4 feet per second, positive 4, because we're going to the right. And here we're going to use the idea that I think we all probably know intuitively, which is, if I told you I'm traveling 30 miles per hour and I traveled for 2 hours, you know that I traveled 60 miles, because 30 miles per hour times 2 hours is 60 miles. And you can even see how the hours cancel out in the product there, the units, and leaving me with just the miles on top as the final units. So we're applying that very same idea here to say over the first 6 seconds of travel, I'm going to go 6 seconds times 4 feet per second as my velocity, and I'll get 24 feet. And the seconds, I can see those disappear, leaving me with just the feet as the final units. Now, in terms of a function and a graph, well, here's a way to represent that. And this is the really important idea that we're going to use a lot. I want to create a velocity function. That's what this v of t is. Think of the input t as time in seconds in this case. And the output v is going to be the velocity at the specific moment in time. So for our function, the domain is going to be from 0 to 6 seconds. And the height of the function is going to be a constant 4. And if you look at this, that gray rectangle that you see in the figure there, that is the area under the graph of the velocity function. It's the area under the curve of the graph. So here's my, I'll highlight this in red because it's the velocity curve. Here's the velocity function right there from 0 to 6 seconds on its domain. And if you look at that area underneath it, so under the curve but above the horizontal axis, above the t-axis, time, this box has an area of 24 because it's exactly 6 seconds wide and 4 feet per second tall. And that's exactly where the 24 feet comes out. The area of this figure is exactly the displacement. And, maybe this feels like, more than enough work for such a simple example where it's a constant velocity, but I'm laying this out very carefully now because this one idea is going to recur over and over throughout these examples. And in fact, this is pretty much the entire Calculus 2 course concept in one slide. This idea that the area under this curve represents the displacement. The area under the velocity curve is displacement. That's a fundamental idea. In fact, it's so important that it's the main idea of the fundamental theorem of calculus. And I picked this first example to be a straight line constant velocity just so that you'll kind of believe me, that you'll understand this idea at a basic level, because now we're going to start to apply it to velocity curves that are changing, that are not constant. So let's do that now. Same thing as before, I'm going to lay out some details and then I want you to pause the video for a minute and think about this. Now that we've seen that first example, try to draw a graph and then think about what the area under that graph is. So let's say we set the marble rolling to the right at 4 feet per second. And then we cause it to slow down. So this is where I needed to say, pretend I have control of the apparatus and I can change the velocity in any moment in time. Doesn't matter how I'm doing it. Just pretend that I'm able to slow it down at a certain rate. So it loses 1 feet per second. Sorry, that sounded funny. It loses 1 foot per second every second. So in other words, it starts with a velocity of 4 feet per second. But then 1 second later, it has slowly ramped down so that it's only traveling 3 feet per second. And then 2 seconds later, it's only traveling 2 feet per second. And so on and so on. And I keep slowing it down. What's going to happen over the first 6 seconds? Make a picture of the velocity graph first, and then think about what that tells me about the displacement. All right, pause here and think about that for a minute, and then come back and we'll talk about the answers. Okay, let's look at this. Here is the velocity graph. Now let's look at the picture first, try to make sense of it before we discuss the formula for it. Look at the green highlights up here. See how that matches up with some of the points on the graph. At time 0, the height of the curve is 4, because that's 4 feet per second, how fast it's traveling. And then 1 second later, it has slowed down to a speed of 3 feet per second, and moving to the right, so a velocity of positive 3. And then at time 2, there it is at a height of 2. And then at time 3, there it is at a height of 1. And then, here's the interesting part, at 4 seconds, it will be momentarily, just for like a fraction of a second, it will just be not moving. It will have a height of 0 velocity. And then if I keep pulling the velocity down, it's going to go negative. And that's what this little section under the horizontal axis, under the t-axis, that's what that means. If I continue this and slow it down, I'm essentially going to cause the marble to roll to the right slower and slower, and then it's going to temporarily stop, and then it's going to start moving backwards to the left. And that's what this section down here represents, backwards motion. For example, at time 5, the velocity is down here at -1. In other words, it's moving to the left at 1 foot per second. And then at the very last moment, it's going to be traveling backwards to the left at 2 feet per second. And now if I look at this red line, this velocity curve, do you see how that's a straight line that starts at a y-intercept of 4 and has a slope of -1 because I'm slowing it down by 1 foot per second? Hey, by the way, that's the acceleration. If you remember from calculus how the rate of change of the velocity is the acceleration. Slowing it down, that's telling me that the acceleration is -1. So in other words, that's telling me the derivative, hey, remember that? The derivative, the rate of change of the velocity is -1. And that's why I'll see it as a line with a slope of -1. Those ideas are connected. And then we'll cut it off at the domain of 0 to 6, just because I only asked about the first 6 seconds. There's no other good reason to cut it off there. That's just what we're curious about. So let's just accept for the moment this idea that the area under the graph represents the displacement. Let's take that idea and see what it tells us. Well, we have two triangles here. This triangle has a width of 4 and a height of 4. So it has an area of 4 times 4 is 16, but cut it in half because it's half of a rectangle, and I get 8. There's that number. And what I have in the line below that is perhaps another way to think about that. If you think about those first 4 seconds, it started at 4 and ended at 0 speed. So on average, it was traveling 2 feet per second for those 4 seconds, and 2 times 4 is 8. Meanwhile, that little purple triangle underneath has a width of 2 and a height of 2, so an area of 2. And remember that it's negative because it's underneath, it's backwards motion to the left. And so we're going to call that an area of -2. And so this is telling me that as this marble is traveling to the right and being slowed down, it's decelerating, and then all of a sudden it turns around and pulls back to the left, this is telling me that it will have traveled to the right for 8 feet and then back 2 feet. And so overall, the displacement is the total, the net area underneath the curve, which is going to be 8 minus 2, or 6 feet. But meanwhile, the distance is going to be the sum of those as if they're all positive, and that's what the 10 feet represents, 8 plus 2. So in other words, the marble is going to end up 6 feet to the right of where it started, but it's going to travel 10 feet on that journey. So I hope those two examples give you enough of the key idea for me to state this general fact here. Let's suppose I have some function, f of x, and just like what we were just doing, I'm going to imagine that it represents velocity, and the x horizontal axis represents time. But I'm only saying this here just to tie it together with the examples we've just seen. As we move on in the course, we're going to generalize this concept to allow x to be not always time, but something, and then the function to represent not always velocity, but something that's changing with respect to x. And then the area under the graph of that function corresponds to the total amount of something. Now in this case, if I use velocity and time, that total is going to be displacement. But in general, we're going to allow this to be kind of like a total change, while the velocity is like a rate of change of something. And if you think about it, the velocity is the rate of change of position for our specific example. And isn't displacement the total, the net change in position? Yeah. So what I'm saying here is that I'm thinking of time, velocity, and displacement, but in general, this same idea applies to any quantity that is changing with respect to some other quantity. Now the picture that I have up here only has the function above the x-axis, and so if it happens to go underneath like this, we would count this area under the curve as negative. That is what I'm trying to say in this line down here. And that's exactly like what we did in over here, remember this previous example, that blip that was underneath the time axis, we counted that as motion backwards to the left, we counted it as a negative area. And if I were counting distance, so total distance, not displacement, what I would do is essentially think of, say one underneath like this, I would kind of think of that area as above and count that as a positive area. Just like what we did down here when I said, let's call that +2 if I want to count distance instead of displacement. And so all of this is based on that fundamental idea that for a constant speed, the idea of distance being rate times time, that applies. And that was true for the area of the rectangle back here. And then I said, let's just apply that for this other example here, even though the velocity is changing over time. But I'm hoping these examples will give you enough of a motivation to believe that. And in the next video, we're going to talk about why that really works when the velocity is not constant, when it's changing, like we just saw in that example, or when it's changing in a curvy way, like I have in this image up here. Why does that really work? Well, we're going to do some calculus. We're going to zoom in, kind of like what you do for derivatives, and you think about zooming in on the function until it looks like its tangent line. We're going to do something similar. All right, I'll see you there.